So I have the 3x3 matrix A 0 0 1 1 0 1 1 2 1 1 2 0, sorry, and I want to do a singular value decomposition of it. So A is equal to U sigma V transpose, where U and V are orthonormal, and sigma, this matrix capital sigma contains the singular values. Yes. So the first thing I will do is I will take the transpose of my matrix A. So A transpose is equal to 0 1 1 0 0 2 1 1 0. Okay. And now I will calculate A transpose A and A transpose. So A transpose A, if you calculate that, you get 1 1 0 1 2 1 0 1 5. And A times A transpose is 2 2 1 2 4 0 1 0 2. Yes. Yes, and now you can find the eigenvalues of those matrices. So I used a calculator to find them because it was really complicated to find a 3x3 matrix where the eigenvalues are simple to compute by hand. I mean, to find out by hand. Yes, so I just plugged that into a calculator and searched for the eigenvalues, and I got that lambda 1 is equal to 5.323, lambda 2 is equal to 2.358, and lambda 3 is equal to 0.319. Yes. And so now I can take find the singular values. So sigma sub 1 is equal to the square root of lambda sub 1. So the square root of 5.323. Sigma sub 2 is equal to the square root of lambda sub 2. So yeah, the square root of 2.358, and sigma sub 3 is equal to the square root of lambda sub 3. So the square root of 0.319. Okay, so you can just take the square root of those values here to find the singular values. And yes, just one thing to notice, you have maybe seen why did I first write lambda 3, lambda 2, and then lambda 1, because why is lambda 1 equal to 5.323 and not something else, and why is lambda 3 equal to 0.319 and not something else? Because remember that the singular values in your capital sigma matrix, they need to be put in descending order, so the biggest singular value comes first, and then the second biggest, and so on, and the last one is the smallest one. So here, if you take the square root of 5.323, you get a bigger number than the square root of 0.319, or the square root of 2.358. And so, yeah, you remember that sigma sub 1, so the first singular value, is greater than or equal to sigma sub 2, which is itself greater than or equal to sigma sub 3. And that's why, the first eigenvalue is to be the biggest eigenvalue, the second one the second biggest, and so on, so that the singular values are also ordered in that rank. Yes, that the sigma sub 1 is the biggest singular value, sigma sub 2 the second biggest, and so on. And remember, one of the reasons why this is done like that is that, like, if you have a computer and you use the singular value decomposition to do some kind of computing algorithm, or I don't know what, the first stretching factors are put first, so those are the biggest singular values, so that in case, for example, that we don't have enough memory for everything and you need to cut out some singular values, we know where to cut. That is, we begin to cut the last singular value because it is the smallest one, so the one that has the least influence on the whole system, and then we cut the second smallest one if needed, and so we immediately know where to cut, where are the least important singular values. That's one of the reasons why we order them in descending order. Sorry, in what happened? In descending orders. Yes. Yes. So now I have my singular values, and my screen is doing strange things. Yes. So now I will find the eigenvectors associated to A transpose A and A transpose. Remember that if you find the eigenvectors, so the eigenvalues are the same for both A transpose A and A transpose. Remember that the eigenvalues are the same, but the eigenvectors are different. And if you find the eigenvectors associated to those eigenvalues, if you find the eigenvectors for A transpose A, you will get your vectors V sub I, so V sub 1, V sub 2, V sub 3 in our cases, so that will be contained in our matrix V, or would I say V transpose. And if you find the eigenvectors for A transpose, you will find those will be the vectors u sub 1, u sub 2, u sub 3 contained in your matrix U. Remember that difference. So A transpose A gives us the vectors inside the matrix V, and A transpose, if you find the eigenvectors, you get the vectors inside the matrix U. Yes. Right, great. So yeah, if you find the eigenvectors associated to those eigenvalues here for A transpose A, you get that you have 3 eigenvalues, so you get 3 eigenvectors. So V sub 1, I will call it prime because it's not normalized. So this is the one of the vector contained inside the matrix V. So V sub 1 prime is equal to those values. Again, I plugged that into a computer because it was really difficult to find first 3x3 matrix where the eigenvalues can be easily found by hand, and more difficult even to find the 3x3 matrix. So if you take if you multiply it by transpose, it's easy to find eigenvectors that are easy to find by hand. So yeah, I just plugged that into a computer. You can do the same thing. Yes. Or otherwise, you can try it by hand if you like a challenge. I don't know. Yes. So V sub 1 prime. So prime because it is not normalized. Is equal to 0.075, 0.323, and 1. Yes. And again, now we will normalize it. So V sub 1 will be V sub 1 prime over its norm divided by its norm. Okay. So just remember, you normalize a vector. A vector is said to be normalized if you take your vector. And you divide by its norm, its length. So you divide here in this case by the square root of 0.075 squared plus 0.323 squared plus 1 squared. Yes. And so V sub 2 prime is minus 1.946 minus 2.642 and 1. And so again, we normalize it. We get that our vector V sub 2 is equal to V sub 2 prime over the norm, so the length of this V sub 2 prime. So the square root. So it will be this vector divided by the square root of minus 1.946 squared plus minus 2.642 squared plus 1 squared. Yes, and V sub 3 is V sub 3 prime is 6.871 minus 4.681 and 1. And so again, we normalize it. We get that our normalized vector V sub 3 is V sub 3 prime. So this vector here divided by its length, by its norm. So so this vector here divided by the square root of 6.871 squared plus minus 4.681 squared plus 1 squared. Okay, so plus a negative value. Yes, for the second. Sorry, I mean it's squared anyway, so the negative value will disappear. So it doesn't matter. Yes. Anyway, great. So now we have our. It's squared by that. I mean, like if you have the square root of something squared plus something negative squared plus something else squared. This value here, if it's negative, it's squared anyway, so we get a positive number. So it doesn't matter. Yes. That's what I wanted to say. Anyway, I'm a bit overcomplicating, I think. Yes, anyway, now we can do the same thing for A transpose. So we get that U sub 1 prime is equal to 3.323, 5.023, and 1. And again, U sub 1 will be the normalized version, so this vector divided by its norm, so the square root of 3.323 squared plus 5.023 squared plus 1 squared. Same thing for U sub 2. U sub 2 prime is 0.358 minus 0.436 and 1. And so U sub 2 will be this vector here, so U sub 2 prime divided by its length, so the square root of 0.358 squared plus negative 0.436 squared plus 1 squared. Yes. And U sub 3 prime will be minus 1.681, 0.913, and 1. So again, the normalized vector will be this vector here, so U sub 3 prime divided by its length, so divided by the square root of negative 1.681 squared plus 0.913 squared plus 1 squared. Yes. And so those will be the vectors inside your matrix U, and here those will be the vectors inside your matrix V that you will then, of course, transpose. Here, if you write it in the form A is equal to U sigma V transpose. Yes, and just for the sake of information, I mean here what I just did is I plugged everything into a calculator, so I got directly the eigenvalues and then the eigenvectors for A transpose A and A transpose. But of course, remember that like in the last videos, if you already found all vectors V or all vectors U, I mean all the vectors contained in your matrix V respectively U, you don't need to necessarily do the whole computation for the eigenvectors for the other matrix. You can simply use those shortcuts that V sub I is equal to 1 over sigma sub I times A transpose times U sub I, and U sub I is equal to 1 over sigma sub I times A times V sub I. Yes. You can do that, but of course I just plugged in everything into a calculator, so I got everything directly. But if you try to do it by hand, you can use that as a shortcut. But of course, remembering that if the singular value is 0, you cannot do that, and you need to do something else. Like in 3 dimensions, you can use the cross product, because you just need to find a vector that is normalized and orthogonal to all other vectors you found. So orthogonal to all. If you need a third vector V, you just need to find a vector that is normalized and orthogonal to the 2 other vectors V you found, and same thing for you. So yeah, in 3 dimensions you can simply use the cross product if the singular value is equal to 0, which is not the case here because we don't have any 0 eigenvalue, and so we have no 0 singular value. But that can happen. Otherwise, if you are in other dimensions, you can use another technique like Gram-Schmidt, for example. I don't know. Yes, and just if you use those formula, it maybe you need to normalize again after you computed those formulas. Like maybe you have your normalized vector U and V, and then you apply your formulas here. Yes, for as said, non-zero singular value. And it may be possible that the vector you get is not directly normalized. Like you get something that is not of length 1. Basically, if you take the length, and so you need to normalize it again. So you again simply divide the vector by its length to get the vector. Yeah. So just check that if you use those formulas. Yes. So now we have our matrix U, which contains the vectors U sub 1, U sub 2, U sub 3. Our matrix V transpose, which contains the vectors V sub 1, V sub 2, V sub 3. So those are vectors, okay, because we transpose it. So of course you can write it in other form. You can write it that V, okay, is equal to V sub 1, V sub 2, V sub 3, and then you can transpose it to get it in that form. It's the same thing, okay. It's just here it's transpose, here not. But yes, it's the same thing, and yeah, those V sub 1, V sub 2, V sub 3, and U sub 1, V sub 2, U sub 3 are the vectors that we found here. Yes. And our matrix capital sigma contains the singular values inside the diagonal, and again from in descending order. So sigma sub 1 is greater than or equal to sigma sub 2, which is itself greater than or equal to sigma sub 3. Yes. Yes, and those values are put in the diagonal. The singular values are put in the diagonal, and everything else is filled with zeros. Yes. And also U and V are orthonormal, as said. So that means that the vectors contained inside are all of length 1 and are orthogonal to each other, as we discussed before. Yes. And yeah, so now we have the singular value decomposition of our matrix A. So A is equal to U sigma V transpose. Yeah, so those are that is our capital sigma, that is our V, respectively our V transpose, and that is our U. Yes. And now, just to finish, so yeah, that's it. I mean, it was hard to find the 3x3 matrix where the eigenvalues and eigenvectors can be computed by hand, so I just plugged in everything into calculator. That's why the values are so strange. I mean, not clean numbers, but yeah, that was to do an example. Yes, so remember the general procedure. You find your transpose, then you find A transpose A, respectively A transpose. You find your eigenvalues. You put them in descending orders. Then you find the singular values, which are simply the square root of those eigenvalues. And then you find your eigenvectors. So for A transpose A, you will get the vectors v inside the matrix V, and for A transpose, you will get the vectors inside the matrix U. Yes, and then you do your computation. And now, just to finish, I want just to show the geometric meaning of what we did, just to make it clear. We already talked a bit about it in the last videos. I just want to remember you of that. What does that exactly mean, this single value decomposition? I mean, we just compute an algorithm by the tip we thought. This has a simple geometric meaning. Yes. So yes. So those u and v are orthonormal. That means that we can use them as a basis in our vector space. So suppose we have some basis u sub 1 and u sub 2. So here we are in 2 dimensions, but of course you can do that for in as many dimensions as you want, but here it's in 2 dimensions for the sake of simplicity. So we have our vector x here, some random vector x, and just I want to notice that I will just, for notation, I will use that this is our vector x, and the first component is x sub 1, but it has a point on it, and the second component is x sub 2, but there's a point of it, on it. And just to just show the difference, those are vector components, while here the u sub 1, u sub 2, v sub 1, v sub 2 are vectors, just for the sake of notation. I put a point here to denote that it's a vector component. Yes. Yes, so I have my basis with my vectors v sub 1 and v sub 2, sorry, not u sub 1, u sub 2, v sub 1, v sub 2. Basically, the single value decomposition tells us that if we have our vector x expressed in some basis v, like I said here, basis our vector x is expressed in the basis v sub 1 and v sub 2, and now we apply our matrix A to it. What it does is our matrix A does two things. It rotates the vector x and it stretches it. It can stretch it by a positive factor, by a negative factor. So that would basically, if you have my vector x here, you can stretch it positively or negatively. That is, you mirror it basically. You can stretch it by a value greater than 1 or smaller than 1, whatever. So it has a stretching factor and it has a rotation factor. So it turns the direction of my vector. So the matrix A does two things. It rotates and stretches my vector x, expressed in this basis v. Now I can simply say that I have my vector x, and I can find another basis u, so here u sub 1 and u sub 2, which basically are the rotation factor of A. Basically, those are the rotated bases. So to represent the rotation that my matrix A does, and the matrix capital sigma is basically my stretching factor. Okay, so how much each of the component of my vector x basically is stretched positively, negatively, by amount greater or smaller than 1, whatever. Yes. So yes. So the rotated basis, so the vectors u are basically the rotation factor of my matrix A, and the single values contained in my matrix capital sigma are the stretching factor of my matrix A. That's basically what it does. Yes. Yes. So yes, should write the x here. So yes. Sorry, not in 3 dimensions, we're in 2 dimensions. Yes. So my vector x. We have like it's really messy. Sorry. Yes. If you express it like that, you can say that the first component of your vector x is expressed in this other basis u, so it will be the rotation basically, and then you stretch that amount by some factor sigma sub I, and you do the same thing for the second component, because you are in 2 dimensions again, and you get the same result as if you simply applied A to your matrix, to your vector expressed in this basis v. Okay, of course v is generally the default basis, so it's simply the vector 0, 1 and 1, 0, respectively 1, 0, 0, 1 in 2 dimensions. But yeah, it could be another basis. Yes, and so yeah, at the end you get that you get your rotated and stretched vector x, so x prime basically. Now it is. So x prime will be yes, I said sigma sub 1 times u sub 1 times the first component of my vector x plus sigma sub 2 times u sub 2 times the second component of my vector x. There should be a 2 here. Yes, so that's the geometric meaning. Basically, it's just that someone noticed that if you have a vector x expressed in some basis v, again, it could be the default basis or something else. If you apply A to it, a matrix A to it, it does two things. It rotates and stretches our vector, and so we can simply say that we can find a basis u that basically is plays the role of the rotation of a matrix A, and the matrix sigma that plays the role of the stretching factor of a matrix A. And all that is applied to the vector x again, of course. Yes. So that's just the tool geometric meaning. I mean, we always compute the single value decomposition algorithm, but it has really a simple geometric meaning. I really hope that it's clear now what I mean. Yes. Yes, so I think that's it. I hope I forgot nothing. I hope it could help you. And yes, thanks for watching.